Hello, this is Jack Jackson. Today we're going to be talking about problem solving and applications of linear relations. We're going to break this lecture into 5 videos, hopefully fairly short. And the first one, this one here, we're going to be talking about some general problem solving techniques and a 6-step procedure to solving application problems. So we're talking about real world problems that will probably be given to you in some kind of words in a paragraph form or something like that, or a few sentences. We'll set out a problem and we'll solve this. And in the process of solving these problems, for the classes that we're going to be doing here in these videos, we're going to be looking at ones that have to do with something about linear relations, linear functions, knowing something about those properties, or possibly something about linear equations and solving linear equations. So this is a good place to start. These steps that we're going to be doing and learning here are some general steps that we're going to apply in more complicated situations later on down the line. So if we can learn how to use these for linear relations, then we're going to be better off learning them in this simpler context, and then we have those tools and techniques available to us when we get to more complicated situations. Now, some of these classes of examples that we're going to be looking at, where we're going to apply these, all of these again have something to do with linear functions or linear equations. The first class I'm just going to call number puzzles. We'll talk about that in the second video. And the number puzzles really are just, in one sense, they're not that important as real-world examples, but they're a good place to start because they get us into the problem-solving technique. And they're fairly easy to see how to apply some of these basic ideas in some real basic setups. Then we're going to look at some velocity applications where we know something about distance, the rate of speed or velocity, and time, and somehow the relationship there, and use that to help us solve some application problems there. We're going to look at unit value applications, things like where we know something like coin problems, how many cents per coin or how many dollars per pound of something that we're making up. And then we'll look at several different examples where we're using percentages and proportional reasoning for these. So here are some basic problem solving strategies. This is not meant to be an exclusive list, but here's a few things that we might do. One thing we might do is look at related problems. So you know, when you encounter a new problem that you haven't seen before, you might say, well, is this like anything that I've seen before? Can I apply anything that I've learned in a math class, in another class, or just in my life? Can I take anything that I know in my little arsenal of tools? What can I use to apply to this problem? And so you might think back to where you've worked a problem that had some similar characteristics. Another thing that you can look at is look at simpler cases. So oftentimes we'll get an example, and maybe it has way too many steps, but we can look at a simpler case, maybe only has 1 or 2 or a few steps, and we can solve that simpler case. Okay, and so then we may look at it then it gets a little bit bigger and a little bit bigger. And so then we can find and generalize some patterns and structure that we see maybe from the simpler cases, and we can move on to a larger case. So in general, this idea of finding and generalizing patterns and structure is an important algebraic idea. Another important algebraic idea that we've talked about is working forwards and backwards. So sometimes if you're not getting anywhere from working from the beginning, you can start at the end and work backwards. If you know sort of where you want to be at the end, you can work backwards from there, and somehow you'll meet somewhere in the middle. Then you can rewrite it in a forwards manner. Okay. Another thing that doesn't need to be dismissed is this idea of just guessing and checking. And so you make a guess, you check it, and if it works, of course, you're great, you're done. But most likely it won't work on the first guess. But look at your guess and say, okay, as I check it, did I notice something about this? Did I guess too high or too low? Can I tell that from the check? So reevaluate, and that will lead you to a better guess. And so you have a loop here of guess, check, reevaluate, guess, check, and reevaluate. And that might eventually lead you to a correct answer. It's not necessarily the most efficient way to go about problem solving, but sometimes it is effective, at least to get you going to get some ideas. Definitely make good use of illustrations, graphs, pictures, diagrams, tables, and of course if we have technology available to us, we can use that, whether that is a graphing calculator or the computer or whatever. Okay, maybe some physical manipulatives. And then one of the things that's very, very important is to persevere. Persevere in problem solving. So keep working, keep after it. Don't give up if you don't get it just immediately. So the more advanced the material you're working with, the longer and harder the problems will be, and the longer it will take you to figure out what to do, especially in a real-world setting. So keep after it, keep working. That's very important. So now I want to go over a 6-step procedure to solving application problems. And I found that this 6-step procedure is very useful in solving a wide variety of application problems, not only for mathematics classes, but also for science classes and business classes, for social science classes, etc. Any kind of situation where we have any kind of numerical relationships, this 6-step process can be very helpful in solving the problems. So the first thing you want to do is read the problem. Then you want to reread it, and as you go through the second time, you're going to organize your information. You'll write down the known and unknown values. You will draw a picture or graph and label its parts. Write a formula, equation, inequality, or system of equations, and write that down. And then, step 4, solve the formula, equation, or inequality, or system. Perhaps make a table in there, might be part of that. And then you'll want to write down your answer. And then check your answer. So let's talk about each of these steps in a little more detail. So the first step is read the problem. Now the first read through, you just want to get a general understanding. Don't try to solve it all at once. You just want to get a basic idea of what the problem is about. Nothing to write down here, just simply read it, and you're reading the language of the problem. And if possible, you might say, well, this falls into one of the categories that I already know about. And if so, that might help you get started on step 2. Okay, so you just want to basically read the problem, get a basic understanding, and kind of identify a little bit of what it is you're looking for and kind of what you have. Next, and this is probably one of the most crucial steps right here, you want to organize the information as you reread the problem. So you want to read the problem at least twice and maybe even more. And so there are 2 parts of this that you want to work through simultaneously. Write down the known and unknown values and draw a picture or graph and label the parts. So let's talk about the writing down the known and unknown values. So this is to organize your information into easily usable fashion. So you should be able to reconstruct the problem from the information you write down here. So just looking at what you write down in step 2, I should be able to look at that and tell you what the original problem said. Okay, but it's going to be a little bit more organized than it might be given to you. It might be given to you in some sort of free-flowing paragraph. This is going to be a little bit more organized. So there's sort of 2 ways to do this, and we'll see some examples of each of these as we go through this series of videos. So one way you can do is list the information in 2 columns separated by a column of equals. So you've got a column of equals in the middle. On the left will be what it is in variables, and on the right will be what it is in words. So fill in the right column with words, like it may say width, or it might say number of items. And then on the left side, you're going to give that a number if you know what it is. Like if you know the width is 7 feet, you write 7 feet. Or maybe you may just write 7, and on the other side say width in feet. Somewhere or another you have to have the units. Okay, if you don't know what it is, you might give it a letter, and you usually try to use suggestive letters. So if you don't know the width, you might just call it W. Now sometimes here, instead of just using a single number or a single letter, we might put a variable expression. So for example, if you know the length is twice the width, and you've already put down W for the width, instead of making length be L, that's one possibility, but you could also go ahead and use that relationship that the length is twice the width to go ahead and write the length as 2W. That sort of thing. So you want to write it as an expression of variables and numbers, constants, or just a constant number or just a variable. You can do this with multiple variables, but a lot of times I find it's easier if you try to limit your variables as much as possible. Now, if you find yourself listing the same information over and over again for different things, like say we have a okay, let's just take a little simple kind of puzzle problem where we're mixing up a bunch of coins, and we've got the value. We have the name of the coin, you know, like pennies and nickels and dimes and quarters. And then we have the unit value for each one. We have, 5 cents per nickel, 1 cent per penny, 10 cents per dime, and 25 cents per quarter. And then we've got the number of pennies and nickels and dimes and quarters. And then we have the amount of money that we have in pennies, nickels, dimes, and quarters. So notice we're asking the same information over and over and over and over again. Well, once about pennies, once about dimes, once about nickels, etc. And so what we can do here, rather than having this huge long column with all this, it makes more sense to organize this in a table or a chart. And so instead of doing it in the two-column form, like I said here for A1, in A2 you can do this as a chart. And so we're going to see some examples of both A1 and A2 versions, the two-column thing with the column of equals, and then we'll also see some more larger examples where we have a chart is very helpful. So the charts are extremely helpful. And so it's very important that we put all this down and label everything very carefully. Now while you're doing this, you also want to draw a picture or graph and label its parts. Now sometimes this is optional. For example, you're talking about a young person and an old person. Drawing a little young stick person and an old stick person is not necessarily helpful. You can do it if you want, but it's not necessarily that helpful. But sometimes this is extremely important. I remember taking a class in physics one time where we were looking at a complicated diagram, and in fact, I might draw several diagrams. I drew a diagram, and then I drew a diagram of a part of that bit larger diagram, and finally I isolated a part of that maybe was a triangle. Okay, then I could work with the triangle because I knew some properties of triangles. So you want to do that at the same time, okay? And or it might be if you have a formula that you can go ahead and draw a graph or make a table of values. Also, some of this can be organized in this part here. Now, up to this point, steps 1 and 2 are just about. There's really not that much mathematics per se. It's just a matter of organization. Step 1 was about just being able to read the problem. Step 2 is about taking what you've read and organizing it. Now there's some mathematics there in applying variables and variable expressions, but mainly it's just organization. Number 3 is where your knowledge of the subject matter really comes into play. So if you're in a physics class, this is where you know something about physics, or chemistry if you're in a chemistry class, or something about business. This is where you know, for example, that simple interest equals the amount of the interest equals the principal times the interest rate times the time. That's where you know that fact from business. So this is where you know a fact from geometry, like the area of a rectangle is length times width, or whatever. But this is whatever your subject matter, this is where your knowledge of the subject matter comes into play. And so you use that to look back at your things that you have organized in step 2 and write a relationship, an equation, possibly an inequality or a formula or a system of equations relating the known and unknown values. Now it's really a good idea to write down this equation in words first, And then where you see word expressions, you can substitute in their constants, variables, or variable expressions that you have set up in step 2. So this is going to be writing an equation. My experience is most students, if they can write the equation down right, they can get the rest of the steps. They have to be able to write the equation down, but if they can do that, solving the equation, there's some skill involved there, but it's a skill that most students can master. They can check the equation. They can do the rest of the steps. It's getting the right equation down that's the key. And really the key to getting the right equation down is back in step 2 where we organize our information. So step 2 is the crucial step along with step 3. Okay, once we do that, then we want to solve that formula or equation or inequality or system of equation. Now here we might use any kind of algebraic methods and steps we've learned. Okay, so far we've learned a few for linear equations. As we go through the course and learn about other types of functions and relations, we'll be looking at some other types of techniques that we might use algebraically, but you can use any of those. Here in a section or two we'll be talking about solving systems of equations. If you have that, you can use those methods. We can also use, if it's available, calculator or computer methods, algebraic, numerical, graphical methods, or any combination of methods that we know. So this is where we really know something about our mathematical techniques, both technology techniques and by hand techniques. Possibly we might have to use the regression capabilities of a calculator to model a set of data to get approximate solutions. So sometimes it's not possible to do exact values, but we can approximate things. We'll talk about what I mean by regression and modeling in a little bit later section of this unit. It may involve evaluating a formula or a table or a graph at particular values. Maybe it's where we know an input, we want to find an output, or where we know an output and we want to find an input. And sometimes approximate answers are all that's possible, and sometimes approximate answers are all that is needed. Now at this point we may end up with an answer like x equals 3. But x equals 3 is not an answer to the problem. It's a solution to the equation perhaps, but the problem probably didn't even have an x in it at all. That's probably something we introduced back in step 2 where we identified what the x represented. When we go to step 5, we want to write down the answer. Now this involves more than you might think. It sometimes involves interpreting the answer. For example, a negative might indicate down, whereas a positive might be up, or a negative might be that we lost money, whereas a positive might mean we gained money, or many other things that we might interpret. Sometimes we might even have to eliminate answers. Sometimes this doesn't happen for linear equations, but maybe for some types of equations we might look at later, there might be multiple possible answers. Maybe you have a positive answer and a negative answer, say for a quadratic application, for example. Well, if it's supposed to represent a temperature, then positive and negative values are both possibilities, and maybe there are two possible answers. On the other hand, for example, if it's supposed to represent a length, then a negative answer would not be appropriate. And so you just throw out that as a possible solution and only keep the positive one. If you end up having to eliminate all the answers, then you have a solution that is not even possible. Now, another thing you want to be sure that you do is include the appropriate units. Okay? So, you say the distance is 4. Well, what is it? 4 centimeters, 4 meters, 4 miles, 4 inches. There's a lot of difference in all those measurements. So we have to be sure that we use the correct units. Okay, and finally, we want to write our answer in a sentence, because the problem was probably given to us with some sentences. So instead of saying something like x equals -3 for an answer, our answer might be the speed decreased by 3 miles per hour. And see, that's written more in terms of what the original problem might have done. Sometimes our answer may also include a graph of some kind or a table of values. Now, at this point, if no one ever made mistakes, we could probably stop. But we want to check our answer for step 6. Okay. Now, the first thing you want to do is a quick check to see if it's even reasonable. Use so-called common sense. Okay. Is it even reasonable? I remember seeing some problems where students came back and they said, okay, this was a problem had something to do with distance and the rate of speed and the time, and they worked that all out, and they came back and said the average speed was 375 miles per hour. I said, dude, he's on a bicycle. Does this make sense? Doesn't even make sense, okay? So make sure the problem makes sense in the context, okay? So don't abandon the common sense. Also, do a complete check to see if the answer is actually right. Now, don't go just back to your equations and plug in your numbers. As I said before, usually students solve the equations right. What's the problem, if there is one, is because the equations are set up wrong. So you can check the numbers in the equations to see if you solve the equations right, but that's still not checking the problem. Checking the problem is, with the answer that you have in hand, go back and reread the original question and see if the answer makes sense and work through the logic of the entire problem from the original equation. So again, here are our 6 steps. Read the problem, organize the information. To organize the information, you're going to do 2 parts. Write down the known and unknown values, perhaps in a table, perhaps just in columns. And along with that, if needed, you're going to draw a picture or graph and label its parts. Next, write a formula, equation, inequality, or system equations relating the known and unknown values. Next, solve the formula, equation, inequality, or system of equations. Okay? And finally, write down the answer back in a sentence form and interpret it. And then check your problem by going back, not only to make sure it makes sense, but check it back in the original logic of the problem. So the next thing we're going to do is we're going to illustrate this problem-solving technique by applying it to a wide variety of situations. Now, since this unit is about linear relations, we will begin by investigating a number of basic problem types that result in linear models, linear equations, linear inequalities, or linear type system of equations or inequalities. Now, in spite of the fact that linear equations and linear functions are the simplest type of function, they have a wide variety of number of basic applications. In each of these cases below, we will have something that serves the role of slope. So recall that the slope is the rate of change, or average rate of change, in the function, and that linear functions have a constant slope. That is, linear functions are functions with a constant rate of change. Remember that the slope has units, which are units of the output over the units of the input, because it is, after all, delta y over delta x. So it's y units over x units. Now, in the beginning of the examples that we're going to be looking at in our next video, they are probably easy enough. You can just completely solve them in your head without writing anything down, or at least some of them may be. However, that's not what we want to do here. The goal is to try to go through this 6-step process, and we're learning the general problem-solving process. That's much more important than the answer to the question. In fact, some of the questions we're going to ask at the beginning are just kind of silly puzzle questions that nobody really cares the answer to. What we're doing is we're using those to just help us learn this general problem-solving strategy. So once we learn the problem-solving strategy method on the easier problems, then as we get to the harder problems where we really need the method, we'll already know the method. We'll just have to learn how to apply it in the more difficult situations. Okay, and these steps that we're going to talk about, these same 6 steps on the 6-step procedure for problem solving, again, this can be used in many, many fields, not only mathematics, but anything that results in analysis of data, including physical sciences, physics, chemistry, other sciences, biology, medicine, business, social sciences, psychology, etc. Just about any area that has something to do with numbers in your problems, you can use these steps. So our next we'll follow this up with 4 more videos with looking at applying these steps in some different classes of problems.